Hello. So welcome to the next section of CS229. So what we're going to talk about in the next series of about 4 lectures is the start of unsupervised and kind of less supervised learning, and I'll make that concrete. And kind of the plan is what you're going to see is you're going to see a bunch of things that look like various different ways of dealing with this fundamental problem of what do we do when we don't have labels, right? So we're first going to look at an algorithm called K-means, and then we're going to look at this algorithm called GMM, this Gaussian mixture model. Those will both happen today. And we'll try and put those algorithms on kind of solid footing in the maximum likelihood framework, okay? We'll then see a couple of more algorithms that have to do with this unsupervised way of viewing the world. One of them you're going to use in your homework called ICA. It's actually, the reason I teach it, it's kind of a fun algorithm. It's a weird bit of setup, but it's probably people's favorite homework problems when we look through the kind of feedback. It's a fun problem if you remember the cocktail problem from the first day, where you have people talking in a party, and you have microphones scattered around the edge, and you want to know who said what. You want to do what's called sometimes source separation, and understand the sources. So we'll do that in the ICA section. And then we'll talk about a more advanced topic called weak supervision. Weak supervision is industrially used to create large training sets for big deep learning models, which you've just come out of that. But these are labels that are lower quality than the traditional supervised labels. And then finally, we'll talk about self-supervised learning, which is really exciting and is one of the big revolutions in machine learning, where we train on something simple like predicting the next word. And if we train on enough data, we can use it for all of these other, sometimes called downstream tasks. Okay? So that's kind of the program for the next 4 or 5 lectures. And today we're going to start with those basics. Okay, so we're going to start with the basics as unsupervised and work our way up to pretty modern stuff. And I will say, historically, I would say 5 years ago, I kind of didn't like teaching unsupervised because it felt kind of squishy and weird, to be honest with you. It didn't have the beautiful theory, or maybe even 10 years ago, didn't have the beautiful theory of supervised learning where you could say, like, this is the right model and we go find it in a lot of cases. But that's been where almost all of the research activity, not only in my group, but kind of from AI over the last 3 or 4 years, has been in this unsupervised realm. So we'll start with some of the classics and get our way to something really, really exciting. Okay? So the classic, and probably an algorithm you already know, or probably you can guess kind of how it works, is this algorithm called K-means, all right? And then we'll get to these other ones. But this is the one we're going to start with first. So what's the difference? So in the supervised setting, right, we get points. And the key issue is that the points come with labels. So you have labeled these plus and these minus, as we were doing. And we would draw a line or a boundary in between them. That was the way we formalized a wide variety of learning tasks, okay? Right? And the point is those pluses and minuses, those are labels, right? And unsupervised started in this setting. I give you the points, but I don't tell you any labels underneath the covers, okay? Now, there are many things on the spectrum between I give you the labels perfectly to I don't show you any information about the labels and I just show you the data points. And we're going to talk about that spectrum, but now we're going to start in the cleanest setting in unsupervised where we just see those points, okay? Now, the thing that you should calibrate here is like, what can we expect as an answer? So in the supervised setting, as I said, it was super clear what we wanted. Like, we could talk about what this line is, and we can go deeper and deeper into like why that's the right line, why that's the right separating hyperplane. In the unsupervised case, it's necessarily squishy, and we'll talk about the ways in which it's squishy. And what I mean by that is it's harder in some sense. So unsupervised learning is harder, and what I really mean by that than supervised. What I really mean by that is we have to allow stronger assumptions, okay? Stronger assumptions, right? So one of the things that kind of pass by you without thinking about it too much in the supervised setting is you're like, there's just some data and there exists a separator, there exists some class. That's pretty weak for what we had to assume about the data. For unsupervised, we're going to have to assume there's some kind of latent or hidden structure. And a lot of the conversation is, hey, if that structure is there, can I provably recover it? That's the kind of thing that we're going to do. And we're going to trade off kind of assuming more about our data and trying to find it robustly, okay? And now, compared to supervised, we're also going to accept weaker guarantees, okay? So weaker guarantees. So in supervised learning, in many cases that we cared about, weaker guarantees, we would say, like, we got exactly the right answer, right? This was the right model. We could say, you know, there was some theta star out there that was just the right thing we were looking at. As we'll see, and I'll show some examples in a second, in this unsupervised world, it's not super clear what the right answer should be all the time. If I just show you this picture and say how many clusters are there, some of you say, well, there's 2 clusters. Some of you say, well, why aren't there 6? There's 6 points. Why isn't each one in its own cluster? And if we'll see in some examples, it's not really clear what there is. We have to make some assumption or do some modeling to understand and kind of get to the bottom of our data. Okay? And so that's what I mean by weaker guarantees and stronger assumptions. And we'll see those mathematically, but just keep them in the back of your head. We're going to be more comfortable saying, like, what if our data are generated this way? That's going to be a stronger assumption. And then we're going to say, we can recover something that's pretty good some of the time. All right. This is less jarring to you than it was like historically, honestly, because historically we would teach the first part of supervised learning without things like neural nets and all the rest. And neural nets, you kind of got comfortable with the fact that, like, hey, maybe it's computing something useful, maybe it's not. We don't know. We just run it for long enough. Okay? This used to be a little bit more disturbing. Okay? So if you look at the literature, you'll see that in it. So let's start with our first version of this. All right. So what we're going to be doing is we're going to be given some data. Oops, it's not very, doesn't look very nice. This is our given data, okay? Given. And we have some points. And this is basically me just introducing notation and copying what we had before, all right? We're also here, as I mentioned, that stronger structure, we're going to also be given a parameter which says how many clusters we think there are. So the game is going to be, here I'm going to write down, k is equal to 2. And our goal is that what we want to do here is find a good clustering, right? And so our do is, we want to use I'll use colors here. Apologies, hopefully it'll be obvious. You don't need to know what the colors are. But we'll kind of find 2 colors like this. Say, like, in what sense is this kind of intuitively good? Okay? This is the same thing we were doing in supervised learning, right? We're like, this is an intuitively good thing. We talked about different loss functions. And you're kind of an old hat at that. So you can kind of imagine what we're going to do. Like, oh, the loss in some way from some object shouldn't be too far away. Now, the K-means is hinting at that object is going to be the mean or the center of that cluster. You kind of want to minimize that center cluster. That's not obvious? We'll come back to it. Okay, so this is what we're given. Given data, we're given this K parameter, and our goal is to create some clustering that we're going to talk about. So we need a little bit more notation. Okay. Now, this guy we'll call some point x1. We'll call this point, say, x3. And that's just the notation that's there. I'm going to write the notation formally in a second. Okay? But before I do that, is it clear kind of what the setup is? You give me some points. You don't tell me any labels. You'll also tell me how many clusters you're looking for. And then it's my job to find them, find those clusters. And we'll talk about how to make that precise and formal in a second. Awesome. So I'll just write down some notation. And if there are any questions, please pop in them.
Just one question.
Sure.
Why are you calling it x1, x3?
I'll show you that notation in just one second. So yeah, let me write the notation down, then I'll come back to what I'm calling there. Great question. Also on the ed thread, sorry that I forgot to do it earlier. Someone's asking, what about the unknown k case? We'll come back to how to select k later. Some of our algorithms, as we'll see, just to go ahead, some of our algorithms will actually have a natural test for k. We'll be able to basically try all the different k's and pick one. Some of them will not, and it will be a modeling decision. And let's come back to that question for how k is unknown. It's not, by the way, it's not super unrealistic that k isn't known. You may know by looking at your data that roughly you think there are about 3 or 4 products or something that people are talking about or various different topics. And those are the kinds of situations you will need kind of k-means in. But let's come back to it. Great question on the ed thread. All right, so let me give you some proper notation so we can actually talk about this maybe a little bit more mathematically. We won't be super heavy on that today. Okay? So what we're given in general is some x1 to xn that live in some vector space. And here we're given some k, which is the number of clusters. Okay? Number of clusters. Okay. We need one bit of notation to do this. So how am I going to make these colors into notation? Well, I'm going to introduce this thing. We're going to find an assignment. Find an assignment of points to clusters. Of points to clusters. Okay? So how do we do that? To the k clusters. So what we're going to have is we're going to have a map that's called ci equals j, means point I to cluster j. Okay? So here I is going to run from 1 to n, and j is going to be from 1 to k, right? These are the same. This k and this k are the same. Okay? So back to this, I was drawing, I got a little ahead of myself. I started to draw the notation before giving it. This is just saying we can call this point x1, this point x3. I'm just noting down what the points themselves are. And then what our goal is to find this map that I drew by kind of this highlighted color, and that's going to be this Cij character here. So this is, I'll highlight it in yellow for reasons, I'm not really sure why I picked yellow. Okay. So for example, C3 equals 2 encodes this fact that C3 is in cluster 2, and I made the green cluster 2. So 0.3 in cluster 2. Okay? Okay? This will sound kind of opaque at the moment, but this is a hard assignment. We're saying every point belongs to exactly one cluster. And the reason I'm signaling that is in the end of the lecture, we'll talk about a soft assignment, where we have a different version of this. Okay? But that's what this is. Anything that's obtuse about the setup? All right, let's see an algorithm. All right, so let me copy this piece. All right, drag it over there. All right, get rid of these characters because we don't see them. And this is our input, okay? So the question we want to ask is, how do we find the clusters? Find the clusters. Now, there are many ways to do this. And if you're a complexity kind of nerd, then you would say, like, is there a polynomial time algorithm for this and all the rest? The answer is no. Actually, it turns out there's an NP-hard problem. So we're going to have to use a heuristic-based algorithm to do this. And let's see the most natural kind of iterative approach here. Okay. So how does it work? Okay, so here's the idea. We're going to start by randomly picking cluster centers. And then what we're going to try and do is, the way we're thinking about K-means is, we're going to try and find our clusters as that are described by 2 cluster centers. So intuitively, let me just jump back, sorry about this, jump back. We'll kind of try and find a point, say like here, and a point here, that are good cluster centers. And they're cluster centers in the sense that all the points in their cluster are closer to the center than they are to any other center. Okay? And that's how we're going to construct our Cij. So we'll start by picking these means. The means, where are we going to pick? If we knew where to pick them optimally, like, we'd be done. So we just pick them randomly to start with. So I'll pick the cluster center for 2 up here, and I'll pick the cluster center for 1 down here. Oops, I'm going to use a different color for deep-seated reasons. No, for no reason. I just like different colors. Okay? Sound good? So I just picked those points. Maybe I want to move this one just to make my life a little bit easier. I'm going to delete that and drag it over. You say, why are you dragging it over? Because it's like a cooking show, and I want to make it just look a little nicer when I draw the pictures. Yeah.
So the cluster centers have to be selected within the list of points that we have, or they can be...
No, these were not lists of points. These are just 2 random initialized points in the plane. I just randomly picked them in RD. We'll talk about a smarter way to initialize them in a second, but just for the moment, they're just random points. They are not points. They do not have to be points in that you were given. We'll talk about how to initialize them later, and you may not exactly want to do that, but you want to do something similar. Okay? So let's see how the algorithm runs. So the first thing is, what would the clustering be if these were the centroids? These were the center points. Oh, go ahead.
Oh, sorry. What is the name of the algorithm?
K-means. Sorry, yeah, I wrote it above it. This is called K-means. Great question. Please.
How do you, I guess this is a simple case, but if there's a more complicated data set, how do you determine what K?
So for the moment, K is going to be given to us as input. We'll come back, as I talked about how to select K in a minute. But let's run through the algorithm once and see how it works. Then we'll talk about kind of what goes wrong and how to extend it. These are wonderful questions, really great questions. Are there others? Awesome. Okay, we'll come back to that. And please, both questions, please come back to those, as I said. All right, so the first thing is we have these randomly centered cluster points. Okay, so this is our first step of the algorithm, is that we're randomly initializing cluster points. Randomly initialize mu1 and mu2. Copy, paste. Oops, got more than I bargained for. Boom. And this one. Paste. Okay, so we just randomly initialize where those characters live. Okay. 2. We then assign each point to a cluster. Okay? And the way we do it is, which point are you closest to? So I think, if my drawing's okay, those are all, closer to mu1. And maybe this one and these couple are closer to mu2. Okay? So you're clear enough what I've done? This is the cluster assignment. And I can write it kind of mathematically in 1 second. If you'd like, I'll vamp a little bit and say how I did this more precisely. Max over j, 1 to k. Oh, sorry, min. What did I write max? Arg min. C, or mu. Let me write this clear. What's going on? Mu j minus xi. Okay? I'm going to put a square there just because I like squares. Because we do it. Not really too problematic. So, and they're the same distance. So this says Ci, where I'm mapping the ith point, well, I just find the closest mu j to it, my current mu j. Okay? That's the way I'm doing the assignment. Every point goes to its closest neighbor. And I'm like arbitrarily saying this guy's closer than mu2. All right, now I have to improve my clustering, because remember it's iterative. So what do? I'm going to copy it so I don't have to overwrite it. What happens? Well, what do you think I should do? I should probably take the points that I have and compute a new center, my new guess of the center of the clusters. So what I do is I compute new cluster centers. What does that mean? Cluster centers. So I'm going to move, I look at mu here. What's the new cluster center for that? Boom, boom. Well, it looks like it should be somewhere here. Right? This is where mu1 goes. And where should mu2 go? Well, probably somewhere right here, right? That's kind of the mean of them. Okay? Now you can compute these things precisely, but I'm just drawing them, just so you get an intuition. Okay? And I'll write this notation because there's more notation. So now I have new cluster centers. Now what's the next step? I repeat. So I go back and I assign every set that's closer to mu1 or mu2. So now I have these characters, and I have these characters there. Okay? That's now doing step 2 again. I repeat step 3. What's going to happen? They're going to jump to the spot in the middle and the spot in the middle. mu1 is going to be there, mu2, and then there's going to be no more change if I were to continue running the algorithm forever. Okay? So let me write that out mathematically while you digest that statement, but that's the entire algorithm. Okay? So what does this mean? Mu j is going to equal 1 over sigma j. It's going to be some average over all the points in sigma j xi, such that sigma j is just the set of points I such that ci equals j. Okay, this is just some notation that says these are all the points that are closest to the center j, and then I average over all of them. I just compute their mean, hence k-means. Okay? I iterate this thing, and I repeat until no assignments change, until nothing changes, basically. Repeat until nothing changes. Notice that if the labels don't change in step 2, then the mean is not going to change, because it's a function of the labels, right? It's a function of like what I guessed was in each cluster. It's always their mean. Any questions about that? Nothing changes. Oh, yeah. Please.
Super open-ended, but how can this go wrong?
Yeah. In many different ways. So let's talk about a couple of things that go right, and then we'll talk about what goes wrong. So the first way it could go wrong is, does it terminate? Right? So if you imagine it was in some, it's not obvious, like I'm doing this kind of jumping around, it could oscillate wildly, right? Like there's nothing that like prevents it, at least at a high level when you're thinking about this, of going like, oh, one switched from red to blue, then it switched back from blue to red, and then the cluster centers are like jumping around and they're in some unstable kind of equilibrium. So that's something that potentially could be bad that happens. So that's the first question, does it terminate? Does it terminate? All right, and it turns out, this is great, yes, it does. Now, why does it? The reason is that this functional underneath the covers, 1 to n xi minus mu ci, that is, the distance between a point and its cluster center is actually monotonically decreasing. Okay, it's not increasing. So that oscillation can't happen, basically. And you can basically view the algorithm underneath this, K-means, if you really want to be kind of super abstract, you can view it as basically doing gradient descent on this object in a particular way. See the nodes for actually the convergence. So it converges to something, okay? Now in unsupervised learning, that converges to something is about is kind of what we can hope for. In particular, you may also ask, well, okay, it converged to something. Does it converge to a global minimizer? Does it converge to global minimizer? And if I did my job setting this up, your intuition should say, no. No, not necessarily. Now you may look at this and say, well, not necessarily. Maybe there's a better algorithm out there that, given this setup of problem, you just, why did you pick this algorithm? It's a bad algorithm. You should show me a better one. There isn't a better one because it's actually NP hard. If you don't know what that means, don't worry. There's no hardness proofs in this class. It does not really matter. It just means we don't know, like humanity does not know a better algorithm for this that runs in polynomial time. Okay? And we have reason to suspect there isn't one. Okay? All right? So this algorithm, as I said, like it's going to run, but sometimes it can end up doing things that are like, quite bad. In particular, it gets stuck by like getting a cluster over in a region where it should have never been, and if it like had more carefully searched, potentially it could have gotten a lower cost solution. All right? Clear enough? Clear enough on its properties? Now this is going to be a hallmark of what we do over the next couple of lectures. Almost everything we do, with the exception of one algorithm that we'll talk about, has this property that it doesn't necessarily converge to a global optimized solution. And as I said, this used to be much more disturbing to people, but now most of AI is in that mode, so people don't seem to care as much. Okay? Used to be quite disturbing. When I started, it was quite disturbing. Now, no one cares. You folks are old hats at this. Go ahead.
So I'm wondering, what will this K-means method converge to the global minimize? So
what happens in that situation? So you can imagine situations, for example, imagine there are points that are really far away and then some other cluster of points here, and that really there's enough kind of things in the middle that the optimal is actually closer to the line. Then what you'll see is that you could end up with some kind of local minimum where you pick a center way over here and a center in the middle of this, but you should have, there was a kind of a better one closer. So that's very hand wavy. I can post some examples where you can actually run through and convince yourself. All that I really care to get across in this lecture, and I couldn't think of how to like get good examples to look at there, is that this is a possibility. You shouldn't expect it to get you a global minimizer, and we have some theoretical reason why we don't believe such an algorithm could exist, even in this simple case. Yeah, wonderful. Okay, now, a couple of side notes. So these questions already came up, so these are really great. So they're not even side notes, they're just responding, they're just being responsive, but I was gonna talk about them no matter what. The question was asked, how did you initialize? Right? How did you pick these points? And from my argument, as I just talked about, even very intuitively and informally, the initialization matters quite a bit. Right? If you initialize way in crazy ways, then you force K-mean to kind of jump back, and maybe there's only one point. Like imagine there's a cluster of points, and you throw one of your centers way across the room. It's going to potentially pick off nothing, and then it's going to have to kind of crawl its way back in some sense. So the point that I care about you getting is how does initialization matter? And I won't go into too much detail, but I want to tell you that there's one algorithm that was developed by smart Stanford students a while ago, maybe 12 years ago? I don't know, 12, 15 years ago maybe even, called KMeans++. And I'll just tell you what they did from great Stanford students. And basically what they decided to do is that they compute kind of a density estimation, and then they place their centers with respect to the density to kind of spread them out in a nice way in K-means++. And without going too much into the details, what ends up happening is they get an improved approximation ratio. So if you don't care about this kind of theory stuff, don't worry. But they're able to show that if you initialize in this way, even though it's NP hard to find the exact solution, they can find kind of a low-cost approximate algorithm to it, provably. So this is actually, when we're talking about what could go wrong, this is something that can go wrong, and what people do in K-means is they used to just kind of run it many times, but if you run with this initialization, it's still a random initialization, but if you run it a couple of times, you're going to get a pretty good solution. And because you're already kind of looking for an ill-defined kind of objective, that turns out to be about okay. Okay. Now, weirdly enough, like I used to, as I said, I didn't really like this stuff, but I wrote a paper about using some of it inside some of making these machine learning models robust, maybe a year or two ago. So it is something that like, I've actually used and care about. Like it does work, and you use it as a way to inspect your data off it. Like you look at your data set and you kind of do your K-means clustering, then you can use that to figure out like, what are the different groups that are inside, okay? All right, this thing here became the default in scikit-learn. And sklearn. So these folks wrote this beautiful paper, they proved this nice result, and now if you run scikit-learn and run the K-means algorithm, it defaults to using the K-means plus initialization. Okay, so pretty fun. Sergey and folks did that. Anyway, all right, so now there was another question, which was, okay, how do you choose K? Right, this came up both in the ed thread, and it came up in the lecture hall itself. How do you choose K? And here's the problem with choosing K. There's no one right answer. Okay? We'll see other unsupervised algorithms which do give a right answer, but let me just illustrate this for you for 1 second. Suppose I give you this data set. Okay? Okay, there's 2 copies of it. One reasonable clustering is this. 2 clusters. Equally reasonable, excuse me, is this one. 4 clusters. Now, if you think about the algorithm as giving you the right answer of what structure is inside your data, then you really don't like this answer. You say, well, what's the right K? Say, well, it's not the right way to think about it, maybe. The right way to think about it is, given that you have a K, can you use this as a tool to find the clusters that are in there of different sizes? So if you're looking for 5 clusters and you really only found, you look at the 5 cluster and the 4 cluster map, you have to make some judgment about kind of which one is better underneath the covers. And that's why unsupervised learning is kind of squishy, but it also turns out to be tremendously powerful. So we can automate the loop of finding the clusters, but which one is good or bad, you're going to have to use domain knowledge for that in most situations. Right? So this is really another way of saying this is a modeling question. So the one part, even when I didn't really care for, I don't know if I'm telling you the history of how I feel about lecture 11, but you're getting it. So, but one of the things that I did like about this lecture always, or this part of the course, is that it forced machine learning folks to move out of the comfort zone of there's a right answer and optimization will find it, which was very disturbing to me because that's not at all how machine learning works and what you're doing. You're constantly in this regime where you're checking if your model works or breaks or does things. I don't know how much Tengyu subjected you to my crazy slides, but that is the way that you live when you're building these kind of ML systems. You build a model, you have no idea if it worked. You have to check it, you have to look at it, you have to inspect it, you have to measure it. So this is kind of natural, and at least forces you to do that. Okay, that's all I wanted to say about K-means. I want to jump to the next algorithm, which is building towards this larger theory of what we did. And if you can kind of squint, you'll see that it parallels how we taught the supervised learning case. But any questions before I move on? Awesome. Please.
Is this something you might use if you're doing supervised learning, but with labels that you're unsure about?
Oh, awesome. Yeah, great question. So let's say that you're unsupervised. So the way we were actually using it is exactly in that way in this paper. What we were looking for, to be really concrete, is we were looking for what are called hidden stratifications. So these are times when a machine learning model, let's say that it's classifying birds that are on the land versus birds that are in the water. I have more elaborate examples in this. And it turns out that the model sometimes gets confused by the background. And so what you want to do is you want to cluster some notion of those feature descriptors underneath the covers of background descriptors that the neural net has learned to try and find a group which kind of looks like an oddball from the rest. So it's oh, here's all the land birds on land backgrounds. I got them all right. And there's this other weird cluster there that I labeled as land birds, but actually are water birds that happen to be walking on land, right? And so that's the kind of thing you look into your labels or your pseudo labels or your predictions and try and find those. It can either be labels that are given to you by a human or a neural net. And that is that was the use case that I had is exactly what you thought about. Yeah, so that's one of them. You'll typically also run this when you have honestly, when you have data you don't really understand, so like you run an experiment with search traffic or ad traffic or something, and you're like, what the heck are people asking about in this segment? And then you run kind of a clustering to figure it out and say like, oh, this looks like a topic that people are talking about X, Y, or Z, right? So those are the other times that you use it. But noisy labels is a good thing, and that will be a theme for next week's lectures. Great question. Please. Yeah, so the question is, if you pick a larger number of clusters, then like if we go to this example here, the problem is how descriptive does it get? So in 4 and 2, you could kind of eyeball the 2 and the 4 and link them up. But if you start to really jack K up to like 1,000, then it is kind of at the brink of what does it mean to find meaningful concepts, right? So if you're looking for 10 things and you know there are 10 things, you want to find those 10 best groups. If you start to jack it up to 1,000, 10,000, it no longer becomes like human digestible. So that's where the modeling thing comes in. It's kind of like the bandwidth of what you can look at and do this. And traditionally, K-means was not used in an automated loop. It was traditionally used as like a way to browse your data. If the consumer of that is some neural net in the discussion we were talking about, then it kind of doesn't matter. You can jack it up a little bit more. The advantage of doing that is if you put too many centers, they may be too close together. And sometimes what people do is they'll just do a kind of a follow-on pass where they merge some clusters that look like they're kind of not informative, a pruning heuristic at the end. So your intuition is dead on. And like that's the side you want to err on. If you err on the side of too small clusters, what happens? You lump two things together that you could have distinguished, and then you could get like a weird cluster in the center. So clearly you're right. The over-provision setting is much nicer than the under-provision setting. Awesome. Sounds like folks got it. Please.
You just talked about how people combine clusters if they see that they are kind of so do they visualize it and see, and like was there like an algorithm for doing that?
Yeah, so I wish there was one algorithm. So this is something that like people are still writing research papers on. We had an iClear paper on. There's another one coming out from another group, which is great, that we're reading right now. Basically, what people try to do in these things is that data point. So this is kind of an impoverished setting, right? We have data points that are just in RD, that are in a vector space, but those data points usually correspond to something real, like there's an image or text. And so the more modern ways that people do with this diagnosis, like what Sabri and folks did and Maya did in Domino, is they said, oh, we took those points and we embedded the text that's associated with an image and the image itself, and we start to like do kind of search queries on top to find the slices that are underneath the covers. So this is the purest setting where you're just like, I have data in a vector space, but of course, like with modern methods, like there's an underlying object. It's a transaction or an image and a caption, and then you start to use some of the more modern techniques to search through it. And then of course you visualize it or monitor it, and there are a number of tools that are out there to do this. I wouldn't say it's solved, like, oh, you just use X and you're done, but there are a number of tools. But yeah, you do have to look at your data. Like there's nothing that really obviates that. Awesome questions. All right, so let's talk about what appears at first to be a slight generalization. Hopefully it feels like we just relax one little thing, but it gets us closer to a more fancy model that will allow us to do some really fun stuff. Okay, and this is actually pretty fun. So this is a toy example from astronomy. And if you know about astronomy, please don't humiliate me too badly. Feel free to correct me. I have no idea what I'm talking about. But I read the paper and I understood the math, so who cares? So it's a toy example, okay? And it's from a paper from the University of Washington. So I can find the paper again if people are there, okay? So here's the general setup of what they're doing. They have this light detector, this photon counting thing, okay? And they're looking in the sky at various different things. And what they want to do is they have, in this simplified model, there's kind of two celestial objects that could be out there. It could be like a regular star and a quasar, okay? And one of them is going to take the light and it's going to spread kind of evenly in all directions. And another is going to send out relatively concentrated pulses, okay? And what happens is, unfortunately, when those photons come to Earth, they don't come with labels. No one gets to like affix a metadata packet to every photon that hits us. We have to see the photons and figure out like where the hell did they come from, okay? So what happens is we get some data that looks like this. Maybe like this. Okay? And these are all our little photons that are there, okay? So, quasars and stars. Now, okay, and both of these things emit light, but all we get to observe are these photon hits. Okay? All right. So now, what we're going to do in our subtle, oh, please go ahead.
For the K-means, are we assuming a linear decision boundary?
No, we don't have to assume a linear decision boundary. We just have to assume that it's close in distance, right? You can get nonlinear. Right? There's no notion of a decision boundary in particular anyway. Like you can draw like a little Voronoi diagram, but we didn't talk about that. Yeah, very nice question. Awesome. Awesome. So we get these photon hits, okay? So what we want to do is kind of figure out, you know, what these different sources look like. And so this is what we're given. What we're going to do is try and find a soft assignment of these things into Gaussians. So remember what Gaussians look like, right? They basically, to high probability, they look like ovals, right? They can be circles, right? That's what a two-dimensional Gaussian looks like, right? And the variance tells you how stretched it is in each dimension, okay? So like maybe there's a cluster here, and this is a tight cluster, okay? All right, so we'll talk about that in more detail in 1 second. But what we have to do is we want to assign each photon to a light source. But of course, we don't actually, in this case, we don't exactly have perfect information of the light sources either. And so we're going to settle for what we call a soft assignment. Okay? So this is the probability, that point I goes to source J. Okay? And this is our soft assignment. This is called a soft assignment. Okay? Why is it soft? Because we didn't, remember in K-means, we said you must be in this setting. Here we have some probability distribution over it. Okay? All right, so just compare that with K-means. All right. So what are the challenges here? The challenges that we're going to deal with here potentially are, there are many sources. Right? If there were just one source, life would be easy. We would kind of fit the Gaussian. You know how to do that from GDA. You take the mean, you find the variance, you're done. Okay? There are many sources here, but for now we're going to assume we know the source is K. We know K, which is the number of sources. Okay? Let's solve the problem in that setting. Okay? And also the other problem is the sources have different intensities and shapes. Intensities and shapes. Okay? So when I was wildly drawing those ovals, the reason was like, oh, maybe there's a Gaussian that looks like this. Maybe there's a tight Gaussian. I don't assume I know that ahead of time. I just know that they're somehow well described by Gaussians. Please.
I guess KS229 is quasars and stars are the two only.
Oh, no. Great question. So those are the two types of things. I need the number of celestial bodies. So like one reasonable thing would be 3. There's one here, and one here. But K is still going to be picked by a modeling assumption, right? So this curve is hard to generate with a Gaussian in our current setup, right? So there's probably more than one on that side, but that's just intuition. There could be 4 there, 5 there, I don't know. Okay. So let me talk about the assumptions, okay? So we're going to assume it's well modeled. And here we're in, most of what I'm going to do is going to be in 1 dimension, so I'm still just going to introduce the notation in 1 dimension by Gaussian. Right? And you remember that a Gaussian means mu j sigma j squared. Okay? So we're just 1 dimension to make our lives similar in a second. But we do not assume we know how many points, that there's an equal number of points. Number of points is equal. Okay? Now, the reason is, in our setup, the physical reason is like, some point sources are really concentrated and strong and they shoot out tons of photons. And in other cases, they'll shoot out, diffuse photons over a region. They may be farther, closer away, different energy levels, whatever. Mathematically, what I mean is we don't know, when we're going to talk about these Gaussians, the shape may be a Gaussian, but it's only sampled infrequently for source 1, and it's sampled 90% of the time for source 2. Okay? This is formally known as an unknown mixture. Okay? Now, one thing that's nice about this problem in the physics setting is, once I get the values out, so what's the do here? I have to get out these cluster centers that we talked about before, and these probabilities, which I haven't given you notation for, but they're going to be called phi in a second. I can check that of how physically plausible that clustering is, right? So in the K, the reason I like this example is in the K-means, you kind of have to eyeball it. But here, if I have a physics model, I can compute how likely is one clustering versus another, given the data sources that I'm seeing. Maybe have auxiliary information about what celestial objects are in the sky in that particular region, and so I can check this information. Okay? And the physicist in this example could actually check the information. Okay? Please.
What's the range of G?
The range of what?
G.
J. Oh, J is going to range, the same, it's going to range over each number of sources. So we're going to assume that we have this K number of sources here. So J will range over K, just like it did in KMeans. So that's fixed, that's a parameter of the problem. Someone's going to tell me, basically what someone's going to tell me is, there are K sources, don't tell you what their means are, I don't tell you what their variances are, so that's for each one of them, and I don't tell you how often, that's this mixture, they emit light. So what percentage of the points go to source A versus source B? Please.
The assumption 2 is about, we do not assume the number of
So for example, let's imagine that we had a situation like, let me just draw it. So let's say that we had 3 points here, and then I'm not going to draw them all, but like 1,000 points here. So there are 3 points here and 1,000 points here, right? So the clustering that I would want out is one cluster here and one cluster here. But I don't get to see the 3 and 1,000. I'm assuming that they're of unequal sizes. So you could, for example, assume that all the clusters are equal sizes. I'm trying to, and that would be wrong, and that's not the way we'd have the model. That's a fair assumption if you knew that, right? But that would make your life a lot easier. It doesn't make, you have to solve both of these two things. Okay, awesome question. All right, please, yeah. Yeah, we make that assumption kind of implicitly because we don't say how often, like there's no probabilistic model, but we do allow K to have like 5 neighbors and 500 neighbors, right? Center cluster 1 could have 5 neighbors, another one could have 500. So it does parallel K-means, so in that sense it's the same assumption. I'm calling it out here as an extra parameter that we didn't have to think about last time, right? Awesome questions. Okay, let's see some 1D mixture of Gaussians. Mixture of Gaussians is like a very fun and famous problem, by the way. People like work on like which ones you can solve. In theory still, it's like it's actually a fun and interesting problem. We won't do that. All right, so I'm gonna be in 1D for simplicity here because it just makes my notation and drawing easier, because I have to draw distributions, all right? So just make sure it's super clear what we're doing. I think folks sound like they have it. So we have 1D, this is going to be the place where our points live. And then imagine there were 2 Gaussians that were generating data, okay? Now, when I say this is generating data, this is the piece, like when I talked about we're going to allow ourselves to talk about models, we're going to imagine that there's really a model that's underneath our data that's generating it, okay? This is quite a powerful technique. Okay? So how does it work? What we're going to do, our idea for the model is we're going to pick cluster 1 with some probability, let's call it P, or cluster 2 with probability 1 minus P. If we pick cluster 1, we then sample a point. Oops, let me get a thicker thing. All right. Oops, that's probably too thick. And we get a series of points. Okay? That's the thought process that we're going through, right? If we only knew those parameters, we could sample from our model. If we knew the probability to pick cluster 1 versus cluster 2, and then we would sample from it. And there's many different parameters, given that model, that could have generated our data, and we're interested in recovering the ones that are most likely generated our data, okay? Now what we see, unfortunately, is just this, just the points. Okay? So this is the model over here. This is what we observe. Oops, gotta switch back. Just the points in R. Okay? These are the xi's. Now, one thing, and this is going to seem like a trivial piece, but it actually makes our life kind of interesting. What if we knew these points all came from cluster 1, and these points came from cluster 2? Okay, so this is our first observation. Well, if we knew the cluster labels, what algorithm would we run? We just run something like GDA. We would just fit Gaussians to this. We'd be done, right? So if we knew this, we could just solve this instantly. Solve and fit Gaussians. So we compute mu I, mu1, mu2. How do we do that? Well, we would just average up all the things in here, average up all the things in here. That would be our mu's. And we could even compute the sigmas and be done. The challenge is we don't get to see them. We don't get those labels. Challenge, we only see this thing. Okay? This is our first example of a latent model. There's something hidden that we don't observe, and we're trying to estimate the parameters of that latent model. And that'll be a theme for the next couple lectures. Please?
In the previous thing, look at the data, you said you need more than 2 vectors because of the...
Sure, yep.
So should the data be more than the 2, or is this...
No, oh, so this is, yeah, so this was an example to motivate like, hey, this is like a nice picture to look at and kind of get you thinking empirically about what happens. I'm gonna walk through most of these things in 1D because it makes my notation a lot easier. And so there's really no relationship between like these points and the points I showed you before. Yeah, great question. Awesome. All right, so why am I doing it in this kind of like piecemeal way? It's because when I show you the definition, then it has a bunch of notation in it, and I want to show you the simplest version so that then you can generalize it and do all that fun stuff on your own. Okay. All right, but is it clear what goes on here? There's this notion I've introduced and kind of sneaked into you, which is a model, right? There's some parameter p here that picks this side or this side, right? Which is going to be called theta, theta 1 and theta 2, hinting later. I pick something, and then I sample from it. If I knew where the points came from, I could just solve it. But the problem is I have this hidden, how often is everything sampled? I don't know how many points should be in each cluster. And I don't know which points are in the cluster. Not only do I not, I don't know either of those facts. So we have to estimate them somehow from data. That's what we're going to do. Okay, so let's see some notation. And we can come back to this example if there are more questions about it. Okay, so let me be a little bit more precise. So we're given x1, xn, element of R, okay, and a positive integer k, and k, positive integer, or number of sources. And our do, what we're given, what we have to do is we need to find that probability function. Find p such that for I equals 1 to n, j equals 1 to k, the clusters, this is the data, we have an estimate of pzi equals j. This is our notion of soft assignment. Okay, so that's what we're responsible. Okay, and this is, although it's a function, it's discrete, so I can write it down, right? I can just write down the probabilities in a table. We'll later worry about cases that's not the case, but for now we do. Make sense?
I didn't get the difference between J and K. Previously it was like J was the number of sources and K was the number of clusters.
No. So J is a cluster index and K is the number of clusters. So J here says, this says the ith point belongs to cluster J with some probability. J ranges over 1 to K. So they are K clusters.
But in the Quasar charge example, it was like J equals 2 and K equals...
No, K was equal. We never actually were precise about what K is. We had rough intuition that K should be at least 3, and I don't think we actually used J, or if I did, I meant and scribbled it incorrectly, and I apologize. Probably was a wayward I. But I don't see it in my notes, but apologies for that. Yeah. Sorry for the confusion. Please.
As for notation, just clarifying here. Z of I means that the sample I belongs to cluster Z?
Belongs or comes from, yeah, so I'll copy it from here. So, oops. It's this sentence. Probability that point I belongs to, I think it should be, I think is what I meant to write. I think that's better. Probability that point I comes from source. That makes more sense in English. From source J, yeah. Yeah. Source J is the particular source. Always the particular source. So I is always the data, J is always the label for the cluster, and K is always the number of clusters. Please.
So is that an X or the same thing here, right?
That in X. Oh, you mean from the...
Is that an X on what's pictured?
No. So ZI is the assignment. So ZI is the soft assignment itself. XI is the data point. Yeah, sorry for overloading the notation. So the ZIs will always be the hidden piece that says so let me write the next sentence, the next piece, and then we'll come right back to your question. I can see why you'd be confused by that. So let me write the GMM model, and you'll see why these two things are being used according to the GMM model. So ZI is the random variable that this probability, that point belongs to it. It's not the actual point itself. So then, for example, we can talk about the probability of Xi and Zi. This is the probability that given this point, and the Zi is that it belongs to a particular cluster. And we'll write down the model in 1 second. So let me write down the model, and then it'll be clear what this notation means. Okay? All right. This is just Bayes' rule. Nothing fancy here. I said nothing. There's no content. Okay? But I'll use it. Now, Zi is going to be distributed as a multinomial according to some parameter that we'll call phi. And phi, as a multinomial, says that some phi j goes from 1 to k, equals 1, and phi j is greater than or equal to 0. Okay? So Zj, if you like, is that sampling probability. Like it's the likelihood that this particular point came from that place. And Zi is going to be picked with this background probability that we're calling p before. So in our earlier example, there was like p and 1 minus p, were the chance that I sampled from cluster 1 or cluster 2 above here. Okay? These are phi 1 and phi 2. That's what I was hinting at. Okay? And remember, in our model, like I picked Zi, that told me where I was sampling. And then, once I knew Zi, Xi, given that Zi equals j, that means given that it was in cluster j, this is going to be distributed like a Gaussian. Mu j, sigma j square. Okay? So these are all Gaussians. Okay? Now, let me highlight for you the parameters we have to estimate. Highlighted parameters. Okay? Okay. Or this thing. Or this thing. Okay. All right, these are the same color. So what's going on here? This is formalizing the model that we talked about earlier. It's our first kind of hidden model. We never see Zi. We don't observe it in data. We don't get to see the labels. You know, the deity, or whoever is generating this data, generates a Zi and picks one of the clusters. That's its sample for this point. And then it samples from this normal distribution to generate Xi. And if you like, the data we think about as being the remnants of this process. We don't get to see this process run. It gets run ahead of time, and then the data is dropped there. And the reason we're thinking about this model is we say, OK, assuming that the model were like this, could we recover the parameters? Okay? And so that's the sense in which we're assuming there's some structure. And it's pretty reasonable. What it's saying is, look, I don't know how many points come from every cluster. That's because I have a multinomial. And 2, I know that the clusters that I have, they're Gaussian shaped. But I don't know if they're circles or ovals, and I don't know where their centers are. And I'm assuming nothing else about my structure. Can you find it for me? That's your job. Does that make sense? We have to come up with these parameters. We have to find the cluster centers and the probabilities that each are sampled from observing the data. Right? Clearly, if I pick one clustering, the data is going to be very unlikely to have been generated with those centers. Right? Like if I go back here, and I picked a center over here and a center over here, that's less likely than if I put the center here and the center here. Right? It would just explain the data less well. We'll be able to formalize that with maximum likelihood, but I hope that intuition is clear. If it's not, please go ahead, ask me a question. I'm super happy to answer.
Can you explain the variable phi? What that is?
So phi is basically just a bunch of numbers that sum to 1. It's a multinomial. So this is a probability I like if I have class cluster 1. Like so, let's say this is going back here. Let's say this is cluster 1, cluster 2, cluster 3, or source 1, 2, and 3. And lots of points are in source 1. So then maybe phi 1 would be like 0.7, right? Because they're like 70% of the data is there. And 10% of the data is here, and 20% of the data is here. Then the numbers would be 0.7, 0.1, 0.2, roughly. Does that make sense? Yeah. Awesome. All right. All right. All right, so let's do one example. I just want to, I'm trying, let me see, call the ZI latent because we don't observe it. We didn't get to see it, right? We just got to see the points. We didn't get to see which was assigned to which cluster because it's not directly observable. This concept, which seems at this point like kind of strange, I would think about a bunch and we'll see it again and again. This is what we mean by structure. We're like, well, there's some wild collection of points, but like there exists a small number of clusters that are generating them. That's the mathematical embodiment of what, this thing is the mathematical embodiment of that intuition. That's all it is. And we say, if that's the case, then we should be able to recover it. Okay? We should be able to recover those clusters in those situations. And in the physical situation of like light sources, that seems pretty plausible, right? Like, you know, they have different intensities, different shapes, so on. Right? So let me give you one more example just to make sure that all these terms are, this notation is there. And I want you to think in sampling. And let me just walk through, so hopefully these things make sense. So phi 1 is going to be 0.7. Phi 2 is going to be 0.3. Why are those the numbers? Because I'm making them up. That's why. Don't have another reason. Phi 1 is going to be 1. Mu 1 is going to be 1. Mu 2 is going to be 2. And I'm going to set sigma 1 square equals sigma 2 square is about a third, roughly. Okay? So what does that picture look like? Well, here we go. There's 1. There's 2. There's one thing here, if I draw it pretty well. Maybe my drawing is off, but hopefully you get the point. This thing should be about a third. This distance should be about a third. The fact that they're uneven is because I'm a bad artist, not because that's the intention of the thing. This is mu 1. This is mu 2. Okay? And this distance here should be about a third. The 65% thing. It's the standard deviation. Okay? How do I sample from it? First, I pick a cluster. Pick one, either 1 or 2, one of my clusters. I pick the first cluster with probability 0.7, the second with 0.3. Then I pick the relevant mean. So if I picked 2, I will use mu 2. I go over here. Then I will sample from a Gaussian and generate myself a point. Let me here. So 2, use the appropriate Gaussian. Okay? So imagine that this were the process that we're generating your data. You just get to see an instance of the data. Your goal is to say what's the most likely process that generated it. Okay? And that corresponds to this intuition. Like there exist some clusters. So far so good? Oh, and then you repeat. Repeat. Yeah, please go ahead and ask questions.
So the C1 and C2 represent the data.
No, yeah, so that would be if I wrote their probability distributions entirely. These are still unit normal Gaussians. This is a great question. I drew it as 2 Gaussians. I didn't draw the phi 1 and phi 2. I incorporated them just in this first set. So I would pick, phi 1, I would pick 1 with probability 0.7. Pick 1, 0.7, right? And you could imagine reweighting them and normalizing them, but then it just gets a little confusing visually, and I'm not that good of an artist. Yeah. Please. Because we don't know how many points come from every source. So remember going back to this one up here? We had like the, oops, I went way too far back. Ooh. Here, we had lots of points from this one source, and this point, there's 70% coming from here, 30% coming from here, 15 or 20% coming from there. And so we're just not assuming that they have the same. If we force them all to have equally sized clusters, we would probably put 2 cluster centers here if this were 70% of the points. And we would use that to explain our data, and that would be, in this case, suboptimal. Right? That's just our modeling choice. We know that the clusters have different number of points in our application, so that's why we fit them. We can't assume they're the same. If we knew them perfectly, we knew the things, we could sneak them in there, but we'll talk about where we sneak them in later.
So I guess following up on that, the P represents this cluster sizes the mu1 and mu2, and then the mean and the standard deviation all represent
the shape.
Then exact distribution of those points.
They are the shape. Really. Yeah, yeah. Awesome. Sure.
So basically we have P1 discrete representation, but why like the second P is smaller than the first P?
Because I'm a bad artist.
Oh.
This one? Yeah, right?
Well,
That's kind of good, man. I mean,
yeah, but sorry about that.
no, it's fine. Just think around.
Sorry about that. But like, should the second peak be actually shorter than the first peak? Because
Yeah, that's a great question. So you could imagine folding the phi's in to try and make them both probability distribution density functions where there was one distribution density function, and then you would fold them in. I've drawn them crudely, having the same height, and putting the probability function up front to say these are the Gaussians, and then there's a height. But you've got it perfectly. Yeah, that's another way to visualize it, which is, if this is beyond my artistic abilities, like that's legions beyond. So yeah, wonderful question. No, that's fine. I do not have a lot of my ego tied up in that. Yeah.
I'm just kind of confused on the process here. So at this point, like, this is after we've modeled our Gaussians, so now we have the Gaussians we're evaluating.
Yeah, awesome. So what's going on here, the trick that we're going to do is we're going to assume, like, okay, so every time you set one of these values, you give me a distribution, right? That gives me a distribution. So now I have an infinite number of these things that are out there with different settings of phi, different cluster centers, different samplings. So now imagine in your head like I grabbed one of them and then I did the sampling process and it generates some data, okay? Great, so we understand that piece. Now what happens though in our problem is we're going to invert that process. So we see some data, just the xi's themselves, and now we want to select among all of those infinite things that are out there, which are parameterized now by these phi's and mu's and sigmas, which one is most likely the one that generated our data. And intuitively we know, as I said, like if the cluster centers are super far apart and our data is all in the middle, that one's probably less likely than one that has the cluster centers closer. We're going to be precise in a second about how we fit that, but you can kind of see where it's going to come from is this model. So in the same way we used maximum likelihood before, we'll get there, we're going to do a little bit more intuition. We're going to say that the parameters that generated our data are the most likely ones after we've seen the data. So we'll condition on the data and try to invert it to find it. So this thinking of like the latent forward process is super weird, right? And so yeah, you're exactly right. Does that make sense though? We think about the process and then we're like, oh, if we inverted it, that's kind of what it must have been. Right, yeah, go ahead. Yeah, please.
So we kind of almost guess parameters and do that for various sets of different parameters that we see each one when we sample from it most closely matches.
Exactly right. The thing is we want to be exactly right. We could just guess all the parameters or try all of them. Problem is there's infinitely many. So the question is, can we solve them and find them faster than that, right? But if we could just in theory, you know, well, in theory is a weird statement because there's uncountably many of them, but like we could conceptually try all of the parameters and then see which one was like closest in probability, you know, had the highest likelihood score. And we're going to try, and that's going to be our gold standard of what we want to pull out. You got it perfectly. Please.
there's only one value which is always one distribution.
So I'm sorry, I didn't catch the last piece of it.
B only has one value, right?
Right.
So 100%. That's the GA, you know everything.
Yeah, in that case, if there's only one value, then you know everything came from one source, and you're just fitting a Gaussian. And the most likely estimate for a Gaussian is, if you saw from GDA and everything else is, average your data to compute the mean, and then can compute the variance from that. And then you have it perfectly. Wonderful. Awesome, we got this. All right, so let's see the algorithm that does this, because it mirrors our friend KMeans. Okay. We're also studying this, by the way, because this same pattern will repeat itself in our next lecture. It's a famous algorithm, so it's fun to know about. And it's important pedagogically. I don't know if you actually have to do anything with it in the class, and it mirrors K-means. So like, why are you teaching me these two things? They seem to differ in small ways, and that difference, like K-means seems a lot more intuitive than this whole infinite number of models that we're selecting among, but we want to get to that worldview so that we want to relate the two. Okay, so one, there's an E step, okay? So this EM is very famous, and we'll come back to that in a second. Here we guess, just as you put it perfectly, we guess the latent values, which in this thing are the values of the ZIs. Okay? So we guess all of the cluster centers, their distributions, okay? By hook or crook. We just figure it out. Okay? That's our first piece. We'll see how we do that in a more intuitive way. And then the M step, we update the other parameters. So if we knew the distributions, we knew, my observation 1, if we knew where every point came from, then we could just run GDA on it. We could just run, find which Gaussians are in each set. We just fit all of them. There's a slight twist that we're going to not know where precisely every point is. We're going to know them a distribution. So we're going to have to do something a little bit more complicated, but not too much more complicated. Okay. This is our first example of a very famous algorithm. First example of EM. EM is like a very, very famous algorithm that people use for decades. I don't want to oversell it. I have a colleague and friend who says you only run it when you don't know what you're doing. And he's right in the sense, he's kind of a curmudgeon, he's a good dude, but he's right in the sense that if you knew exactly what you were looking for, you wouldn't run this algorithm, but that's precisely where it's interesting, is when you run these kind of EM algorithms. You know something about the setup, okay? All right, so let's see mathematically what this looks like, and in your head, you should be thinking, what did I do in K-means? The E step. So here, we're given the data, and current values, which are guesses, for phi, mu, sigma, blah, 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 all the stuff. Sigma 1, mu 2, whatever, mu 1, all the parameters, okay? And our do is we have to predict zi, okay? For I equals 1 to n. All right? Now, I'm going to introduce some notation here following our notes. Oops. Given xi by mu sigma. Okay? So, what's going on? Okay? This is our goal. Okay? So what do we want? We want to compute these weights, which I'm just giving a new notation to because z's will be changing as we run and all the rest. We're given the data point, conditioned on that, so we know the point we're looking at. We know all the rest of the parameters, the likelihoods, the frequencies with which we're sampling from each one of them. We have our current guess. We have our current guess of where the center of every cluster source is and its variance. And now what we want to do is we want to compute how likely a particular point is to belong to a cluster. Intuitively, if it's really close, the probability should be high to the cluster center. If it's if it's really far away, it should be close to 0, but it's continuous. It's not going to be 0 itself, okay? Because the Gaussian doesn't go to 0, anywhere. Okay? So how do we do this? Well, it's nothing more than Bayes rules. Bayes rule. Okay? Xi. Oops. Sigma. Over. All right. Oops. Okay. All right. So all I've done here is something really simple. I've taken xi, which I've conditioned on it, and I've kind of divided it up. So this is kind of the likelihood of the data being generated with this, which is a probability, and then these two things being jointly done together. And then I'm gonna factor them out as I sum over all of the different probabilities, okay? So this is going to be equal to probability of xi, okay, oops, probability of xi, zi given j, probability of zi, j, over sum. I have to use L here instead of j because I don't want to confuse what we're doing. Zi equals L, comma, the whole thing, P zi equals L. Okay. So the point is, we know all of these functions. Okay, oh sorry. And everything here, by the way, has this stuff. We know all that information, so that's everywhere. Okay? Okay, so we know all of the estimates in our guess. So what is this probability right here? Well, if we knew that it was conditioned that we knew that this point came from the cluster, well, it's just nothing more than our friend the Gaussian, right? This is this character right here, which I'll highlight. This is just a Gaussian. We know that from the model, right? So is this, right? So if I can be really explicit about it, it's like, exp of xi minus mu I square over 2 sigma I square, right? Times some normalizing constant, 1 over the square root of 2 pi, right? So we know what this is. What's this one? Those are our phi's. So this character here, oops, I shouldn't use that color. This is phi j, this is phi l. So I've decomposed the problem, once I know it, into estimating all of these quantities, which I already kind of mechanically know how to compute. Okay? So the key point is we can compute all the terms. Compute all the terms. Now, this isn't super surprising. So maybe you look at this and you're like, wow, that's just a bunch of weird notation. What the heck is he talking about? Look, this is just K-means. It's saying, in some kind of generalized sense, it's saying I need to compute a probability distribution function. OK, K-means doesn't need to do that. But how does it do it? It says, well, I consider the probability that this xi was generated from this j. I know how likely it is that a point came from it. I know, given how likely, once I'm in the point, what the probability of this data point is. And then what I'm going to do is I'm going to compare it to the likelihood from every other cluster. And that's the probability, right? That's all it's encoding. Instead of having that hard assignment and saying which one's closest, like in K-means, this was just a max, said, look at all the other clusters, and you pick the closest one. Now I'm going to average over it, and I'm just averaging over it with Bayes' rule. And it looks like notation. There's a bunch of notation, but it's not super scary. It's just things you know how to compute. Go ahead.
If the point is very clearly near the centroid and has no overlap with other cluster or Gaussians, then would the problem be
They wouldn't be 0, but they'd be very close to 0. So what would happen in that scenario? So in your point, let's say xi is really close to this particular j. So this thing is it's not going to be 1 because the height of the thing is not exactly 1, but it's going to be some high number. Let's say 0.5 or something. So some big, big number, okay? Then over here, let's say phi j, that's the other term. So if phi j were equal across all the clusters, we'll come back to what happens when it's not in a second. If it's equal across all the clusters, we get 0.5 times 1 over 5 or something. There's 5 clusters, 1 over 5. And then we compare that likelihood to the rest of these. And because you said these were really, really far away, what happens here? You get this term repeated, right? So you get exactly that one term, plus a bunch of things which are super close to 0. And so as a result, this thing will be very, very close to 1. Yeah, does that make sense? Now what happens, just in that inference, if phi j were very, very close to 0? So now there's this trade-off. As the point, if the point is there's the cluster center and it's close, but I think it's extremely unlikely, like my phi j is 10 to the minus 10, and I've only seen 1,000 points, I still don't consider it very likely that this source actually generated something, okay, in that setting. And that's all Bayes' rule does, in general, is trade off those two things. Does that make sense? Yeah, awesome. Okay, right. Now, back to the, oh, please.
Yeah, I just have a question. I'm a bit confused on the fact that phi j and phi l, those are actual probabilities, whereas the probability of xi is the probability density.
Yeah. So I use them. Okay, so yes. So you can do this because you can use the likelihood ratios in this way, but and this is the correct thing to do from Bayes' rule, but it's a little bit sticky because this is just a PDF, but the fact that it's normalized up to it allows this thing to go through. But yeah, you're exactly right. Yeah, it's a little squishy, but it works. Yeah. Wonderful question. Awesome. So I hope what you got from this is, and also I wanted to come back. So that whole weird rant about how the data are generated is now mechanically the way the math works. That's why I keep ranting about it. You pick a point, you generate the data, that's assigning the likelihood score. When you wrote the generative model, you told me how likely it was, right? That given you were in a particular cluster that you would generate this point. That's the normal distribution. And then you compared and baked them off against each other. And that gave you a probability distribution. That's it. Awesome. Now, there's the other step. This step is much less interesting. So here, we're given all those Wij's, J, which is our current estimate, est of P, Zi equals J. Okay? For I goes from 1 to n, J goes from 1 to k. Okay? And what we have to do is estimate the observed parameters, the non-latent parameters. Now this is conceptually interesting because, right, we split our thing into latent, which are not observed, the Zi's are not observed, what the probability is that you are in a particular class, and the things we did observe. The frequency, you know how many are in each class, you know their cluster sizes, and all the rest, like you can measure those things, okay? And we'll do that using MLE, because that's the tool we use. By the way, we use MLE a lot in this course, but it's very powerful, but it's not everything. I'll come back to that later. But it's a principle, okay? So for example, what is phi j? What is the estimated frequency? Well, we sum over all the points, I goes from 1 to n, of w, j, I. This is our guess of the fraction of elements from cluster j. We can make this a little bit more rigorous, and we'll do it next time. And the point is you just do MLE. I don't want to go through these calculations because they're kind of boring. But you should go through them at least once. And we can make that rigorous. And we'll do that when we do the MLE thing. So I'll do it in class. So don't worry if it doesn't stick now. We'll do it on Monday in a little bit more generalized setting. But what I hope you get here is if I know the Wij's, I have to compute the estimate of phi j. And then I just average over the probabilities. And we'll do all the math to expand that out. But you already know how to do this. This is just the MLE stuff that you've been doing for the last K weeks. Okay. So far, so good? Please.
So we're going to do this MLE in next class?
Yeah. No, we're not going to be, this is the right answer. We're going to derive this in more generality so that you can solve for a larger class of models on Monday. Awesome, please.
So it's fraction of what from cluster?
Oh, fraction of points. Sorry, that's really terrible. I said elements and then I don't know why. These are the points. Points from, this should be source. I was trying to make source and target independent in my head, and I did not use them carefully in this lecture. Apologies. Fraction of points from source j. Awesome. Is the rough intuition of why this is K-means kind of similar to you? You pick a set of means, which are like your sufficient statistics to describe your problem. Then you re-average over them. And what's going on here is you're picking a set, now instead of just picking centers, you're picking distributions. Then what you're doing is you're re-weighting the distribution, saying if that was really the background probability of all these linkages, then this is what your most likely cluster sizes would be. This is how much points you would have in each. Okay, does that agree with your guess? And you just cycle that again and again until you get back to the guess, the same way you're doing K-means. Awesome. All right. All right. So, yeah, please.
What other EM models are we going to study?
A bunch. Yeah, a bunch. Yeah. So basically, an EM model can be applied whenever you have a latent Z like this, and you want to do some kind of decomposition to it.
Yeah, and it's only for unsupervised learning, or
yeah, it's going to have this two-step pattern where you have a latent variable, and then it's not necessarily, like, there's no requirement that any of this be supervised. In some sense, the latent variable is like your guess at supervision. We'll see ways to inform. So, for example, we'll see an algorithm where the first way it was derived actually did use EM, but there's a more clever way to solve it, provably. But EM is the general form of, like, there's a latent variable that you don't see, and you have a model for it. You estimate that parameter, and then you solve like a traditional supervised machine learning or kind of estimation problem under the covers. And that's very, very general. Your latent variable here is clusters, but we'll see it could be distributions and all kinds of fancy stuff later. Yeah. Please.
And so the answer we see that we estimate the parameter using now I'm wondering how do we use the ML? So I think in the ESTAR we already assume that we have an initial guess of a set of parameters.
Yep. So no, oh, great question. I see where the confusion comes in. No, so here it's like we are almost memoryless. So we had those, phi and sigma and all those other things. And now, just like in K-means, we throw away some information and we try to reconstruct it. And here, given our link of PIs, we try to compute all of those observed parameters, which are going to be the mu's and the sigmas and the phi's and blah, 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 the rest of the observed parameters. So it's like, given the linkage function, we do that again. And then what we would expect is that those parameters will not move around so much over time, and that's when it will converge, similar to the way K-means worked. Great question. Awesome. Please.
Is there like a GMM where you have like better guesses for
Awesome. Yeah. There's not something that has such a crisp solution to my knowledge. I don't actually know one, but that's a really good question. How do you initialize this? And in what situations can you better initialize it? It seems natural enough to think about one, but I don't know a proof for one. Yeah. It's a great question. You can post it on Ed, and I can dig around and see if anyone do that. My suspicion is yes, because K-means++ was such an important thing. Yeah. It's a wonderful idea. Other questions? All right. Okay. So looking at this, I'm trying to think what I should tell you. All right, so we have about 9 minutes left. Let me see. All right, so what I want to do is I want to just tell you the steps that we're going to go through next time, because I think over the weekend this will be too much. Traditionally I teach it Monday, Wednesday, but I'm going to want to redo this, I think. That's what I think. So right now what I want to do is have a detour into one thing that we need, which is convexity and Jensen's inequality. So I'm just going to draw the basics here. And then I'll give you a sense of what the EM algorithm looks like. Now the reason we need this is that this is a key result. And it confuses people every year, so I spend more time on it. And hopefully it confuses them less. Sometimes people say it's trivial, and then I'm very, very happy. So if you think it's trivial, then I did my job. Okay? All right. So what we're going to need to do, the reason I want to tell you this is, what we're going to have to do is we're going to have a mathematical abstraction of like this going back and forth and this guessing back and forth. And that's going to be basically two different functions. One function is going to be a lower bound of the function. There's going to be the actual loss function for the totally crazy probability distribution that has all the infinite models and everything jointly together. Okay? The actual likelihood function. And what we're going to do is we're going to have an approximation of it that says, given we have a particular guess of the zi's, we're going to have this lower bound. And we're going to have to move between the lower bound and the upper bound, and the lower bounding function. And that is going to be facilitated by something called Jensen's inequality. And it's worth understanding because it's something that you can use. So I'll just get started a little bit on it and draw some pictures, and then we'll pick it up next time. Okay? AB element of omega. And I would certainly rather answer questions because we can cut into later lectures, so we don't need to rush. Okay? AB is in omega. Okay, so let me draw this. Okay, so something is convex if the line joining them, is inside them. Okay, so like if I take any 2 points in here, any A and B, and I draw the straight line between them, or in Euclidean space, so it's a straight line, then if it's convex, then no matter which points I pick, the line between them is going to remain in the set. This is a convex object, so like an ellipse or a circle or something like that. In contrast here, if I pick points A and B here, this is not convex. Okay? And these are going to be, yeah, we're going to care about these quite a bit. Okay? So what does this mean in symbols? In symbols, we have to check for all A, B, and omega, which is our set omega, lambda A plus 1 minus lambda B, that's the line between them, is an element of omega. And lambda here is an element of 0, 1. Okay? That's all this picture is saying. This picture and this math are the same. Okay? And you need to check for all, right? Right here, clearly if I put A here and B here, there's a line between them. The reason it's not convex is there exists one pair of A and B for which I go out of this set. Okay? Now, we're going to use it when this bottom piece is a function, right? We think about the function going up to infinity, the graph of the function being convex. And what this tells us is if we look at chords, that is points between the function like this, they should always be lower bounds to the function. And that will be a little bit opaque, but it'll feel like you think about a function that looks like this, the x squared function, that set will be convex. That's the canonical convex function, okay? All right, so what we're going to see is we're going to go from these definitions of convexity on sets to convexity on functions. And that's going to allow us to basically prove the following statement, which we will prove next time, which looks mysterious, but is not. You'll see this, is greater than f of e of x. Okay? So there's going to be, we're going to show next time, just I want to give a little bit of a roadmap. We're going to use this definition of convexity to prove a theorem. This theorem is called Jensen's theorem, and it's effectively immediate from the definition. Like, once you understand the definition of this for functions, if f is convex, this is true, f convex. A function is convex if its graph is convex. And we'll draw that out, okay? Once we know that, we're going to need that for convex and concave functions. That's going to be a key building block for what we do for the next couple of lectures. We've talked about convexity once or twice in the supervised setting, but now we're going to need it in a little bit more detail, okay? All right, so let me wrap up and tell you what we did today so that you remember what I want you to take away. So we started with this idea of the difference between supervised and unsupervised learning. We then went through K-means, which was a really simple heuristic algorithm, but in a hard problem that would find these clusters. We talked about this idea that you needed to be able to model the problem to be able to solve it. You had to input either K or something, and you had to be able to check or at least visually inspect the answer. We then talked about a generalization of K-mean, which is called mixture of Gaussians. And the only generalization was, rather than belonging to a single cluster deterministically, you tried to find this probability distribution over everything. That led to a bunch of notation, but the notation still basically had this two-step procedure underneath the covers of guess the centers and then check how likely they are. The how likely they are in K-means was the distance. In GMM, it had this more complicated probabilistic model. We like that more complicated probabilistic model because it's going to allow us to model even more sophisticated notions of structure. And then I think I'm just going to go through that on Wednesday so that you have all the mathematical details there together, and we'll do a review of that. Thanks so much for your time and attention. Have a great day.